Okay, so we want to spend a little bit of time talking about the Weierstrass substitution. So the Weierstrass substitution is something that's important when we're integrating trigonometric functions, just like when they're on their own. Usually this is helpful when it's a rational function with trig inside of it. So this is a fairly helpful technique, and what makes it really nice is we are able to transform something trigonometric into something algebraic. So it's almost kind of the opposite of what we were doing for the trigonometric substitution. We're bringing in the radicals, we're bringing in x squareds, or well, really t squareds, and we're making stuff a lot easier for ourselves. So this is going to work in some situations. We're not going to spend too much time talking about this because this is a lesser known technique, but we will cover it for a little bit. We'll do one video just to introduce the proof, and then another video to discuss examples, and then we'll move on to partial fractions. All right, so let's start off with the definition for sine. So for this, it's going to be helpful that we consider a triangle, as it always is. Trig has been our friend for the last, 10 or 12 videos. So let's have a look. So for this, we are going to be considering an integral of trig functions. We're going to let tan of x over 2 equal t. So let's set this angle equal to x over 2. Okay, and t is equal to the tangent of x over 2. So the way that it's nice to consider this is that we've got a function, or well, not a function, but we've got the units. That was an awful unit circle. I must do better than that. But okay, we consider a triangle, and the way that it's best to consider is a triangle like this on the unit circle. So we've got a nice right triangle. This guy here is going to be 1. But this height here we set equal to t. So when we set that equal to t, then we can make our substitution for sine. So let's try sine. So sine of x is going to be equal to, well, if we have sine, because we're dealing with x over 2, so we need to turn that into x. So sine of x is equal to sine of 2x over 2, because those cancel. Some are just left with sine x. So we need to do a double angle. So we do sine x is equal to 2 sine x over 2 cosine x over 2. Okay, now we need to determine what sine of x over 2 is. So this is going to be equal to 1 plus t squared. So now we need to determine what we're doing with this. So sine is opposite over hypotenuse, so that's t over square root of 1 plus t squared. Then cosine is adjacent over hypotenuse, so 1 over square root of 1 plus t squared. So we can do that substitution. So this gives us 2 times t over square root of 1 plus t squared times 1 over square root of 1 plus t squared, which is equal to 2t over 1 plus t squared. So that is our substitution for sine. So if we see an integral with sine of x somewhere in it, then we can make the substitution sine of x equals 2t over 1 plus t squared. All right, now let's move on to cosine. So cosine is pretty much the same ballpark, or the same monster. We get our same triangle with sides 1t and square root of 1 plus t squared. And this is still x over 2. So t is still tangent x over 2. Cosine of x equals cosine squared of x over 2 minus sine squared of x over 2. We're using our double angle formulas, which gives us 1 over square root of 1 plus t squared quantity squared minus t over square root of 1 plus t squared quantity squared, which yields 1 minus t over 1 plus t squared. Okay, so that is our formula for cosine. So now if we see an integral with cosine of x dx in it, we can make that substitution. Okay, so now we're still missing something, because even if I do this substitution, I'm still left with this dx term. So we need to determine what that's equal to in our substitution. We need to make sure that everything in our integrand is written in terms of t. So now we need to find our definition for dx. So this, we don't really need to use the triangle. All that we need to do is take t equal to tan of x over 2, and then we're going to do an inverse tangent to get rid of everything. And that's going to give us x over 2 equals tangent inverse of t, and then we multiply by 2, so x is equal to 2 tangent inverse of t. So now we have x and we want to find dx, so we need to differentiate it. If you remember the derivative, so the derivative, d by dx of tangent inverse of x is equal to 1 over 1 plus x squared. And I'll relieve you of the derivation of that coming from implicit differentiation. But anyways, once we differentiate, and then we still got that 2 there, so that goes up top. So that gives us dx equals 2 over 1 plus t squared dt. So with that information, you're ready to do everything, because the substitutions I just gave you, we've got our sine, we've got our cosine, and we've got our dx. We can plug that into basically any trigonometric function. If I give you an integral of like sine of x over, let's say, 1/2 plus sine of x dx or something like that, well, we know we can substitute and put everything in terms of t in these nice algebraic functions. Or if I give you something like tangent of x dx, well, you can just recognize that as doing the sine substitution over the cosine substitution. Or this we will definitely do if I give you the cosecant, cosec dx, the cosecant, CSC.